Hello and welcome to Infinite Science.
There are places on Earth where the planet's deepest forces rise into view, where ancient processes, billions of years in motion, break through the surface and touch the sky. We call them mountains. But what we see when we look at a mountain is only the smallest fraction of what's actually there.
Most of us think of mountains as permanent, fixed, silent monuments of stone that have always been and always will be. But mountains are none of these things. They are alive in ways we rarely consider. They move, they breathe, they grow and collapse and reshape everything around them, including us. What if I told you that the mountains you see today are not what they were yesterday and won't be what they are tomorrow? That some mountains are older than bones, older than eyes, older than the very concept of sight itself. That mountains create deserts thousands of miles away, split continents, guide the wind, and hold entire ecosystems in chambers deep underground where no human has ever been.
There are truths about mountains that almost no one talks about. Strange facts hidden in plain sight. Forces so gradual they're invisible to human perception, yet so powerful they've rewritten the story of life on Earth again and again. So take a breath, settle in, let the noise of the world fall away for a while.
Because today we're going to climb into the quiet mystery of mountains, not with ropes and gear, but with curiosity. We're going to explore what mountains really are, how they shape everything we know, and why these towering structures of stone might be far stranger and more important than you ever imagined.
This is a journey into the hidden life of Earth itself. Let's begin. When you look at a mountain, you see stillness, permanence, something that has always been there and always will be. But mountains are not still. They never have been.
Right now, as you hear these words, the Himalayas are rising, slowly, imperceptibly, but rising nonetheless. Every year, Mount Everest grows by approximately 4 millimeters. That's about the thickness of 4 sheets of paper. It doesn't sound like much, but over 1 million years, that's 4 kilometers. Over 10 million years, 40 kilometers.
Mountains are not objects frozen in time. They are processes, events, slow-motion collisions between pieces of the Earth's crust that play out over millions of years. Think of it this way. The ground beneath your feet right now is moving. The tectonic plate you're standing on is drifting across the planet at about the same rate your fingernails grow, a few centimeters per year. You can't feel it, you'll never feel it in your lifetime, but it's happening, constantly, inevitably.
And when two of these plates meet, when they collide with the full momentum of continental drift behind them, something has to give. The crust crumples, it folds, it buckles upward like a rug pushed across a floor. And over millions of years, those folds become mountains.
The Himalayas exist because India is crashing into Asia right now, this very moment. 50 million years ago, India was an island continent drifting north across an ancient ocean called Tethys. It was moving fast, geologically speaking, 15 centimeters per year, fast enough to cross thousands of kilometers in a few tens of millions of years. And then it hit Asia. The collision didn't stop. It hasn't stopped. India is still pushing north, still driving deep into the Asian continent, still forcing the crust upward. The result is the largest mountain range on Earth, the Himalayas, the Tibetan Plateau. Thousands upon thousands of square kilometers of elevated land, all because one piece of crust refused to stop moving. But here's what most people don't realize. Mountains don't just grow, they also shrink. From the moment a mountain begins to rise, the forces of erosion begin to tear it down. Wind, water, ice, gravity. These are patient destroyers. They work slowly, grain by grain, but they never stop. Rain falls on the peak and dissolves minerals from the rock. Frost wedges into cracks and splits stone apart. Glaciers grind away entire valleys. Landslides carry millions of tons of material downslope in seconds.
Every mountain is locked in a constant battle between uplift and erosion, between the forces deep below that push rock upward and the forces at the surface that grind it back down. Some mountains are winning this battle. They're rising faster than they're eroding. Others are losing. They're being worn away faster than they can rebuild.
And here's the strange part. The faster a mountain rises, the faster it erodes. Because tall mountains intercept more precipitation. They create their own weather systems. They force air upward, cooling it, wringing moisture from it. That moisture falls as rain and snow, and every drop is a tiny erosive force multiplied billions of times. So mountains are not growing forever. There's a limit, a natural ceiling imposed by the interaction between tectonics and climate. Most of Earth's tallest mountains hover around 8 to 9 kilometers above sea level. Not because the crust can't be pushed higher, it can, but because at that height, erosion becomes so intense that it matches the rate of uplift. The mountain reaches an equilibrium, a dynamic balance between creation and destruction. This is what it means to say mountains are alive. They are systems in constant flux. They are not things, but processes. They are geology in motion, written so slowly that human lifetimes can't perceive it. But make no mistake, mountains are moving, growing, breathing, changing shape with every passing moment. Consider the Alps. These mountains are rising at about 1 to 2 millimeters per year in some places. At the same time, they're eroding at similar or greater rates. The net result is that some peaks are slowly growing, while others are slowly shrinking. The mountain range as a whole is in flux, constantly reshaping itself. And this reshaping happens in ways both gradual and sudden. Erosion is mostly slow, a grain at a time, a layer at a time. But occasionally, mountains change dramatically in an instant. A rockfall, an avalanche, a massive landslide that restructures an entire slope in minutes. In 1903, Turtle Mountain in Alberta, Canada, experienced one of the largest landslides in North American history. In just 100 seconds, 110 million tons of rock slid down the mountain and buried part of the town of Frank, killing at least 70 people. The scar is still visible today, a gaping wound on the mountainside, slowly being softened by vegetation, but never truly healing. Mountains are dynamic. They exist in a constant state of becoming, never finished, never complete, always in the process of rising or falling, building or collapsing. And they have been doing this for longer than most people can imagine. How old is a mountain? It's a simple question with a deeply complex answer, because mountains exist in layers of time. Some parts are ancient, others are young, and the age of the rock is not the same as the age of the mountain itself. Let's start with the rock. The stones that make up a mountain can be unimaginably old. Some of the rocks in the Canadian Shield, parts of the Appalachian Range, and the mountains of Western Australia are more than 3 billion years old. 3 billion! That's older than oxygen in the atmosphere, older than complex life, older than anything you would recognize as alive. These rocks formed in the Archean Eon, when Earth was a fundamentally different planet. The continents were smaller, the oceans were warmer. The sky was orange and hazy, thick with methane and carbon dioxide. There were no plants, no animals, no forests, just rock, water, and single-celled organisms clinging to life in shallow seas. And yet, pieces of that ancient Earth still exist. They're not buried deep underground. They're right there on the surface, exposed in weathered mountain peaks that you can touch with your hand. But here's the twist. Even though the rock is ancient, the mountain itself might be young. Take the Appalachian Mountains. The rocks in the Appalachians are among the oldest on Earth. But the Appalachians as a mountain range formed during a series of events starting around 480 million years ago during the Ordovician period.
This was when the ancient continents began colliding to form the supercontinent Pangaea. But before that, there were older Appalachians, different mountains in the same location, made from some of the same rocks but shaped by earlier tectonic events. These proto-Appalachians rose during the Grenville orogeny, about 1 billion years ago. They were enormous, rivals to any mountain range that exists today. But those ancient mountains were completely eroded away, ground down to their roots. And then, hundreds of millions of years later, new tectonic collisions raised new mountains in the same region, mountains built partially from the recycled material of their predecessors. In fact, the Appalachians you see today are not the originals from 480 million years ago either. They're the remnants, the ghosts. What's left after hundreds of millions of years of erosion have ground them down. And here's the astonishing part. When the Appalachians were young, they were taller than the Himalayas, much taller. Some geologists estimate that the ancient Appalachians may have reached heights of 8 to 10 kilometers or more, peaks that rivaled or exceeded Everest. But time is the great leveler, and given enough time, every mountain falls. Today, the tallest peak in the Appalachians is Mount Mitchell in North Carolina, at just over 2,000 meters above sea level, a fraction of what it once was. The mountains have been worn smooth, their jagged peaks eroded into gentle, rounded summits covered in forest. What remains is beautiful, but it's the skeleton of something far grander. This is the hidden story of mountains. They come and go. They rise and fall in cycles that span hundreds of millions of years. The mountains you see today are not the first mountains to stand in those places, and they won't be the last. There were mountains before there were trees, mountains before there were insects, mountains before anything crawled onto land, and in some cases, we can still see them. The Barberton Greenstone Belt in South Africa contains some of the oldest exposed rock on Earth, 3.5 billion years old. These rocks were once part of an ancient mountain range that rose when the planet was less than 1 billion years old, before the moon had fully cooled, before the day was 24 hours long. Back then, Earth rotated faster. A day lasted only about 18 hours. The moon was closer, tides were higher, and in that alien world, mountains still rose and fell, just as they do now. And those ancient mountains are gone now, eroded away, flattened, recycled into new crust. But the rock remains as evidence that they once existed. This is what mountains teach us. Permanence is an illusion. Everything is temporary, even stone. Mountains that seem eternal on human timescales are fleeting when viewed across the full span of Earth's history. They rise, they weather, they crumble, and eventually they disappear. The rock is recycled, the minerals are dissolved and carried to the sea. And millions of years later, new mountains rise from the same material. It's a cycle, an endless, patient cycle, and we are living in just one moment of it. Consider the Ural Mountains in Russia. These mountains formed about 300 million years ago when ancient continents collided. They were once as tall as the Alps or the Rockies, but today they're low and worn. The highest peaks barely reach 2,000 meters. 300 million years of wind, rain, and ice have ground them down to rounded hills. And yet, even as they erode, the Urals still shape the land around them. They still divide climate zones. They still influence weather patterns. They still serve as a geographic boundary between Europe and Asia. Even in their diminished state, mountains continue to matter. This is another layer of mountain time, the life cycle of a mountain range. Birth through tectonic collision. Youth as a tall, jagged range. Middle age as erosion begins to dominate. Old age as the mountains are worn down to hills. And finally, death as they're completely eroded away, leaving only their deep roots buried in the crust. Some mountain ranges are in their youth. The Himalayas, the Andes,
the Rockies. These are tall, sharp, actively growing. Others are in middle age. The Alps, the Caucasus, still tall but being worn down as fast as they rise. And others are in old age. The Appalachians, the Urals, the Scottish Highlands, worn smooth, rounded, slowly disappearing. But all of them, young and old, are part of the same cycle. A cycle that has been repeating for billions of years, long before humans existed, long before most forms of life existed. Mountains have been rising and falling, shaping the planet, creating new landscapes, and vanishing again.
And they will continue long after we're gone. Mountains don't just rise from the earth, they reshape it. They control the flow of air and water. They redirect wind patterns. They determine where rain falls and where deserts form. They influence ocean currents, atmospheric chemistry, and global temperature. In ways both obvious and hidden, mountains are one of the most powerful forces shaping the climate and ecology of the entire planet. Let's start with rain. When moist air moves across the landscape, it carries water vapor that will eventually fall as precipitation. But that air needs a trigger, something to force it upward, cool it down, and wring the moisture out of it. Mountains are that trigger. As air encounters a mountain range, it has nowhere to go but up. It rises, following the slope of the land. And as it rises, it expands and cools. Cold air holds less moisture than warm air, so the water vapor condenses into clouds and then into rain or snow, which falls on the windward side of the mountain. By the time the air reaches the peak and descends the other side, most of the moisture is gone. The air is dry, and that dry air creates what's called a rain shadow, a region on the leeward side of the mountain where precipitation is scarce. This is why deserts exist next to some of the wettest places on Earth. The Atacama Desert in Chile is one of the driest places on the planet. Some parts of the Atacama have not received measurable rainfall in over 400 years. And yet, just across the Andes Mountains to the east, the Amazon rainforest receives several meters of rain every year. The difference is the mountains. The Andes block moisture coming from the Pacific, creating the Atacama. And they block moisture from the Amazon, keeping the western slopes dry. Mountains create ecosystems by controlling water. The same pattern repeats around the world. The Himalayas create the Gobi Desert to their north. The Sierra Nevada creates the deserts of Nevada and eastern California. The Great Dividing Range in Australia creates dry zones in the interior of the continent. Without mountains, the distribution of life on Earth would be completely different. Rainforests would exist in different places. Deserts would form elsewhere. The entire map of ecosystems would be redrawn. But their influence goes far beyond local weather. Mountains also shape global climate patterns. The Himalayas and the Tibetan Plateau are so massive that they alter the circulation of the entire atmosphere. In summer, the high plateau heats up faster than the surrounding lowlands. The hot air rises, creating a low-pressure zone that draws in moist air from the Indian Ocean. That moist air rises against the Himalayas, cools, and releases its moisture as rain. This is the Indian monsoon, one of the most important weather. Without the Himalayas, there would be no monsoon. The climate of South Asia would be completely different. Much of India, Bangladesh, and Southeast Asia would be far drier. The agricultural systems that feed much of the world's population would not exist. The civilizations that arose in these regions would never have developed in the same way. Mountains don't just affect local weather, they create entire climatic zones. But there's more. Mountains also influence the chemistry of the atmosphere itself. When mountains erode, they don't just wash away into rivers. The minerals in the rock undergo chemical reactions with rainwater, a process called chemical weathering. One of the most important reactions is the breakdown of silicate minerals, which absorbs carbon dioxide from the atmosphere. Here's how it works. Rainwater is slightly acidic because it contains dissolved CO2 from the air.
When this acidic water interacts with silicate rocks and mountains, it dissolves the minerals and forms bicarbonate ions, which are carried by rivers to the ocean. In the ocean, those bicarbonates eventually combine with calcium to form limestone, locking the carbon away in solid rock on the seafloor.
This process removes approximately 0.3 gigatons of carbon from the atmosphere every year through silicate weathering alone. It doesn't sound like much, but over millions of years, it adds up. This is one of the planet's primary mechanisms for removing CO2 from the atmosphere over geological time, and it's driven by mountains. The faster mountains rise, the more rock is exposed to weathering, and the more CO2 is pulled from the air.
This is why mountain building events have been linked to ice ages. When the Himalayas began rising 50 million years ago, the increased weathering may have drawn down enough CO2 to cool the planet significantly. Some scientists believe this was one of the key factors that ended the warm, ice-free climate of the early Cenozoic and ushered in the cooler climate we know today, complete with polar ice caps and glacial cycles.
Mountains cool the planet, not just by their elevation, but by their chemistry. And their influence extends even further. Mountain erosion supplies minerals and nutrients to the oceans. Rivers draining from mountains carry sediment rich in iron, phosphorus, and other elements essential for life. When this sediment reaches the ocean, it fertilizes marine ecosystems. Phytoplankton bloom, fish populations thrive. Entire ocean food webs depend on the minerals washed down from distant mountains.
In fact, some researchers have found correlations between periods of increased mountain building and increased ocean productivity. More mountains mean more erosion. More erosion means more nutrients in the ocean. More nutrients mean more life.
In this way, mountains feed the sea. But perhaps the strangest influence mountains have is on the movement of tectonic plates themselves.
You might think that tectonic plates move because of forces deep in the Earth's mantle, and that's partly true. But mountains play a role too. When a mountain range forms, it adds enormous weight to the crust. That weight presses down on the mantle below, influencing how the mantle flows. In some cases, the presence of a mountain range can actually slow or redirect the motion of the tectonic plate it sits on.
There's also a concept called gravitational potential energy. Tall mountains are literally higher in the gravitational field than surrounding lowlands. This creates a force that pushes outward from the mountain range, like a column of stone trying to collapse under its own weight. This force can influence how the crust deforms and how plates move. Mountains, in other words, can influence the very forces that created them. This is the feedback loop that defines our planet. Mountains shape climate, climate shapes erosion, erosion shapes mountains, and the cycle continues endlessly across millions of years. Nothing on Earth exists in isolation. Every part of the system affects every other part, and mountains are one of the central gears in that vast planetary machine. Even the rotation of the Earth is affected by mountains. When a large mountain range rises, it redistributes mass on the planet's surface. This changes the moment of inertia, which can very slightly alter the Earth's rotation rate and the wobble of its axis. The effects are tiny, measured in milliseconds over millions of years, but they're real. Mountains are not passive features. They are active participants in every major Earth system: climate, ocean chemistry, tectonic motion, the carbon cycle, the water cycle, biodiversity. All of it is shaped, influenced, and controlled in part by mountains. And all of this happens silently, invisibly, without fanfare. Mountains do not announce their influence. They simply exert it, day after day, year after year, millennium after millennium. Mountains are barriers. They divide the world into distinct regions, separating climates, ecosystems, and species. But they are also islands, pockets of unique habitat surrounded by lowlands, where life evolves in isolation, adapting to conditions found nowhere else on Earth. The higher you climb, the stranger life becomes. At low elevations, mountains are often covered in forests. trees that thrive in the warmth and moisture of the foothills. But as you ascend, the environment changes. The air grows thinner, temperatures drop, the wind intensifies. At a certain elevation, trees can no longer survive. This boundary is called the tree line. Above it, the world transforms into alpine tundra, a realm of low shrubs, grasses, lichens, and wildflowers that cling to life in one of the harshest environments on the planet. And yet, life persists. Not just persists, but thrives in its own way.
Consider the snow leopard, a solitary predator that roams the high mountains of Central Asia, hunting in conditions that would kill most animals. Snow leopards live at elevations up to 5,500 meters, where oxygen levels are half what they are at sea level. Their lungs are enlarged, their blood carries more oxygen per liter than lowland mammals. Their fur is thick enough to insulate them in temperatures that plunge to -40 degrees Celsius. Their paws are wide and covered in fur, acting as natural snowshoes.
They are shaped by the mountain, molded by its extremes. Or consider the bar-headed goose. This bird migrates over the Himalayas twice a year, flying at altitudes where commercial jets cruise. They've been observed flying above 7,000 meters, where the air is so thin that most animals would lose consciousness. Their hemoglobin has a higher affinity for oxygen than other birds. Their mitochondria are more efficient at producing energy in low oxygen conditions. Even their breathing patterns are adapted. They inhale and exhale more frequently than other birds to maximize oxygen intake. Every cell in their body is optimized for survival in the death zone of the sky. Mountains create evolutionary pressure unlike anywhere else, and that pressure produces life forms that seem almost alien. But altitude is only part of the story. Mountains also create isolation. Imagine a species of insect living on a mountaintop. The peak is its entire world. It feeds on the plants that grow there. It mates, reproduces, and dies, all within a few square kilometers. And a few kilometers away, on the next mountaintop, another population of the same species lives in the same way. But those two populations never meet. The valley between them is too hot, too dry. The habitat is wrong, so they remain separate, isolated. And over thousands of generations, they begin to diverge. Mutations accumulate, behaviors change. Eventually, they become distinct species.
This is called Sky Island biogeography, and it's why mountains are hotspots of biodiversity. Each peak is a refuge, a laboratory of evolution, a place where life can experiment with new forms, free from competition with lowland species. In the mountains of New Guinea, there are species of birds found on a single mountain and nowhere else on Earth. In the Andes, there are frogs that live only above 4,000 meters in tiny highland streams. In the Ethiopian highlands, there are rodents that have lived in isolation for so long they've evolved into entirely new genera. The gelada baboon is found only in the Ethiopian highlands, nowhere else. It has adapted to life on cliff faces, where it sleeps at night to avoid predators. It feeds primarily on grass, an unusual diet for a primate. Its chest is bare and red, used in social displays. Every aspect of its biology is tailored to its mountain home. Mountains amplify diversity. They create pockets of uniqueness scattered across the planet, like islands in the sky. But life on mountains faces a challenge unlike any other. Mountains are dynamic. They rise and fall. Glaciers advance and retreat. Climate shifts. And when the environment changes, species adapted to narrow conditions have nowhere to go. During the Ice Ages, many mountain species were pushed off their peaks entirely. Glaciers covered the high elevations, forcing alpine organisms down into the valleys. When the ice retreated, they climbed back up. But some didn't make it. Some went extinct. And those that survived often found themselves trapped on isolated peaks, surrounded by warming lowlands they could no longer cross. Today, as the climate warms again, alpine species are climbing higher, following the cold.
chasing the conditions they need to survive. But eventually, they'll run out of mountain. There's only so far up they can go.
This is the paradox of mountain life. Mountains create diversity by isolating species, but that isolation also makes them vulnerable. They are specialized, adapted to narrow ranges of temperature, elevation, and moisture, and when those conditions change, they have limited options. The American pika, a small mammal that lives in rocky alpine habitats in western North America, is already feeling the effects. Pikas cannot tolerate prolonged exposure to temperatures above 25 degrees Celsius. As summers grow warmer, populations at lower elevations are disappearing. They're retreating upslope, concentrating at higher altitudes where it's cooler. But eventually, they'll reach the summit, and then there's nowhere left to go. Yet, even now, mountains continue to harbor life in places you wouldn't expect.
There are microbes living in cracks deep inside mountain rock, surviving on trace minerals and no sunlight. These are called endolithic organisms, organisms that live inside stone. They extract nutrients from the rock itself through slow chemical reactions. They can survive in temperatures near freezing and in near total darkness. Some of these microbes may live for hundreds or even thousands of years. There are insects that live their entire lives under glaciers, feeding on wind-blown organic matter that accumulates in meltwater channels. Ice worms, for example, live in glaciers in the Pacific Northwest. They emerge at dusk to feed on algae and pollen that has blown onto the ice. If the temperature rises above a few degrees Celsius, they die. They are so adapted to cold that warmth is lethal to them. There are fungi that colonize bare rock at 6,000 meters, breaking down minerals to extract nutrients. These fungi are pioneers, the first organisms to colonize new terrain exposed by retreating glaciers. They slowly break down the rock, creating the first thin layer of soil that other plants will eventually grow in.
Life finds a way. Even in the most extreme corners of the mountain world, something is alive. And perhaps most surprising of all, mountains contain ecosystems we're only just beginning to discover.
In the Alps in the Himalayas, researchers have found vast networks of caves carved into the limestone by ancient water flows. These caves are dark, cold, isolated from the surface for millions of years. And inside them, there are entire ecosystems, unique species of invertebrates, fish, and microbes that evolved in total darkness. Some of these species are so different from their surface relatives that they appear to have split off millions of years ago, during periods when the caves were first forming.
In Romania, there's a cave called Movile Cave that has been sealed off from the outside world for over 5 million years. The only entrance was discovered by accident in 1986. Inside, researchers found an entire ecosystem that survives without sunlight. The base of the food chain is not plants, but chemosynthetic bacteria that produce energy from hydrogen sulfide gas seeping from the Earth's interior. Feeding on those bacteria are worms, snails, spiders, and insects found nowhere else on Earth. Species that evolved in complete isolation, in a world lit only by the faint glow of chemical reactions. They are blind, colorless, elongated, adapted to an environment so alien that it resembles what we imagine life might be like on other planets. Mountains are not lifeless. They are vibrant, complex, and full of surprises. They create conditions that challenge life to its limits, and in doing so, they reveal what life is truly capable of. When you look at a mountain, you see the part that rises above the ground, the peak, the slopes, the visible stone. But what you see is only a fraction of the mountain. Beneath the surface, mountains extend deep into the Earth's crust, far deeper than they rise above it. In fact, the roots of some mountains reach down 70 or 80 kilometers into the mantle, 7 or 8 times deeper than the peak is tall. Why? Because mountains float. This might sound strange.
Rock is heavy. Mountains are made of rock. How can they float?
The answer lies in a concept called isostasy. It's the same principle that makes icebergs float in water. You see only the tip above the surface. The bulk of the iceberg is submerged, hidden below the waves. Mountains work the same way, except instead of floating in water, they float in the semi-molten rock of the Earth's mantle. Here's how it works. The Earth's crust is not uniform. It's made of different types of rock with different densities. Continental crust, the kind that forms land masses and mountains, is relatively light. It's made mostly of granite and other low-density rocks, with a typical density of about 2.7 grams per cubic centimeter. Oceanic crust, on the other hand, is denser. It's made of basalt, which is heavier, with a density of about 3.0 grams per cubic centimeter. Beneath the crust is the mantle, a thick layer of hot, solid rock that behaves like a very slow-moving fluid over geological time. The mantle has a density of about 3.3 grams per cubic centimeter. The crust floats on top of the mantle, and the depth to which it sinks depends on its weight and density. Now, imagine building a mountain. As tectonic forces push the crust upward, creating a peak, you're adding mass to that section of crust. It gets heavier. And just like loading more weight onto a boat causes it to sink deeper into the water, adding mass to the crust causes it to sink deeper into the mantle. This is why mountains have roots. For every kilometer a mountain rises above the surface, it must sink several kilometers below. The exact ratio depends on the density of the rock, but a good rule of thumb is that mountains extend downward about 5 to 7 times deeper than they rise upward. So when you look at Mount Everest, standing nearly 9 kilometers above sea level, you're looking at a structure with roots that extend 50 or 60 kilometers into the earth, an iceberg of stone, most of which you will never see. And just like an iceberg, if you remove the visible part, the hidden part rises. This is exactly what happens as mountains erode. When wind and water wear away the peak, they remove mass from the top of the mountain. The crust becomes lighter, and because it's floating in the mantle, it responds by rising up, like a boat that's been unloaded. The mountain rebounds. This is called isostatic rebound, and it's why some mountains take so long to erode. As you grind down the peak, the root rises to replace it. You're not just wearing away the surface, you're fighting against the buoyancy of the crust itself. The Appalachians, those ancient eroded mountains we talked about earlier, are still rebounding. Even though they haven't been tectonically active in hundreds of millions of years, they're still rising. Slowly, a millimeter or two per year. Because the crust beneath them is still adjusting to the loss of the material that's been eroded away.
It's like trying to push a beach ball underwater. You can push it down, but the moment you stop applying force, it bounces back up. Mountains work the same way. Erosion pushes them down by removing material, but isostasy pushes them back up. Erosion and uplift are locked in a slow dance. One removes material from the top, the other replaces it from below. And the process can continue for tens or even hundreds of millions of years after the tectonic forces that created the mountain have stopped. But mountain roots do more than just provide buoyancy. They also anchor the crust. Mountains are not evenly distributed. They form along the edges of tectonic plates or in zones where continents collide. And the deep roots of these mountains help stabilize the crust in those regions. They act like anchors, preventing the surface from moving too easily. In some cases, mountain roots are so deep that they extend into the upper mantle, where temperatures are high enough to partially melt rock. This creates pockets of magma that can rise through the crust and feed volcanic activity. The Andes, for example, are not just a product of tectonic collision. They're also shaped by volcanic eruptions driven by the subduction of oceanic crust beneath South America. The roots of the Andes interact with this subduction zone, channeling magma to the surface and building volcanoes along the range. Mountains, in other words, are connected to the deepest processes of the planet. Their roots reach into a realm of heat and pressure that no human will ever experience directly. A world of slow-moving convection currents, chemical reactions, and phase changes in minerals that we understand mostly through theory and indirect measurement. Scientists study mountain roots using seismic waves. When earthquakes occur, they send waves rippling through the earth. These waves travel at different speeds through different types of rock. By measuring how long it takes waves to travel from one seismic station to another, scientists can map the structure of the crust and upper mantle. And what they've found is that beneath every major mountain range, there's a deep root extending far into the mantle.
These roots are not uniform. They're complex. They contain folds, intrusions, and variations in rock composition. They tell a story of collision, compression, and deformation that played out over millions of years. And yet, those deep roots shape the surface world in profound ways. They determine where mountains rise and where they don't. They influence the location of earthquakes and volcanoes. They control the flow of heat from the interior to the surface. Mountains are not just surface features. They are three-dimensional structures that extend through the entire thickness of the crust and into the mantle beyond. They are bridges between the surface and the deep earth, and understanding them requires thinking not just about what we can see, but about what lies hidden beneath, in the darkness and heat of the planet's interior. Humans have always been drawn to mountains, and mountains have shaped us in return. For most of human history, mountains were barriers. They divided tribes, cultures, and civilizations. The Alps separated Roman Europe from the Germanic tribes to the north. The Pyrenees divided France from Spain. The Himalayas isolated the Indian subcontinent from Central Asia. Mountains created natural borders that were difficult to cross, and those borders became cultural boundaries that persist to this day. But mountains were also refuges. When empires expanded, when wars raged in the lowlands, people fled to the mountains. They built villages on remote peaks and in hidden valleys where invaders could not easily follow. Mountains became places of sanctuary. And in that isolation, distinct cultures, languages, and traditions developed. The Caucasus Mountains, for example, are one of the most linguistically diverse regions on Earth. In an area smaller than California, there are more than 50 distinct languages, many of them unrelated to any language spoken outside the region. This diversity exists because mountains isolate communities. Each valley becomes its own world, and over centuries, that isolation produces linguistic and cultural divergence. The same pattern repeats around the world. The highlands of Papua New Guinea contain over 800 languages among a population of just 8 million people. The mountain regions of the Andes preserve indigenous languages and traditions that have been lost in the lowlands. The mountains of Central Asia and the Himalayas harbor distinct ethnic groups, each with their own customs, beliefs, and ways of life. Mountains protect culture. They create pockets of diversity in a world that increasingly tends toward homogenization. Mountains also shaped religion. In almost every culture, mountains are sacred. They are the homes of gods, the places where the earth meets the sky. Mount Olympus in Greece, Mount Fuji in Japan, Mount Kailash in Tibet, Mount Sinai in the Middle East. These are not just geological features. They are spiritual landmarks, symbols of transcendence, power, and mystery. Why? Perhaps because mountains are liminal spaces. They exist at the boundary between the known world and the unknown. They rise above the familiar landscape into the realm of clouds, wind, and thin air. They are dangerous, unpredictable, awe-inspiring, and humans have always associated such places with the divine. Mountains are where prophets go to receive visions, where heroes journey to prove themselves, where monks retreat to meditate in solitude. There is something about the altitude, the silence, the sheer scale of mountains that invites introspection and wonder. In Christianity, Moses received the Ten Commandments on Mount Sinai. In Islam, Muhammad received his first revelation in a mountain cave. In Buddhism, the Buddha achieved enlightenment after years of ascetic practice in the mountains. In Hinduism, the Himalayas are the abode of Shiva.
Mountains are not just physical places. They are metaphysical spaces, bridges between the earthly and the divine. But mountains have also shaped human survival in practical ways. Many of the world's great rivers begin in mountains. The Ganges, the Indus, the Yangtze, the Colorado, the Nile. All of them are fed by snowmelt and glacial runoff from high peaks. Without mountains, these rivers would be seasonal streams, running only during rainy periods. But mountain snowpack acts as a natural reservoir. It stores water during the winter and releases it slowly during the summer, providing a steady flow year-round. This steady flow allowed civilizations to flourish in places that would otherwise be too dry. The irrigation systems of ancient Mesopotamia, Egypt, India, and China all depended on rivers fed by distant mountains. Those mountains were invisible to most people living in the river valleys. They might never have seen them, but their entire way of life depended on the water those mountains provided. Even today, billions of people rely on mountain water. The Himalayas supply water to nearly 2 billion people across Asia. The Andes feed the rivers that sustain cities and farms along the western coast of South America. The Rockies provide water to much of western North America. Mountains are the water towers of the world. And as glaciers melt and snowpack diminishes due to climate change, the future of those water supplies is uncertain. Mountains have also been sources of wealth. Ore deposits are often concentrated in mountain regions, where tectonic activity has brought minerals from deep within the earth to the surface. Gold, silver, copper, tin, and countless other metals have been mined for mountains for thousands of years. Entire economies have been built on mountain mining. Towns sprang up in remote valleys wherever ore was found, and when the ore ran out, the towns were abandoned. The California Gold Rush, the silver mines of Potosi in Bolivia, the copper mines of the Andes. These were not just economic events. They were migrations, transformations, moments when mountains drew people from all over the world, promising fortune and delivering hardship. And yet, people kept coming, because mountains hold resources that lowlands do not. But perhaps the most profound way mountains have shaped humans is psychological. There is something about standing in the presence of a mountain that changes you. It makes you feel small, not in a diminishing way, but in a way that puts your life into perspective. Mountains remind us that we are part of something larger, that the world existed long before us and will continue long after. This feeling has a name. Researchers call it awe, and awe is a surprisingly powerful emotion. Studies have shown that experiencing awe makes people more generous, more cooperative, and more willing to help others. It reduces stress, it increases feelings of connection to nature and to other people. It can even temporarily reduce chronic pain and improve immune function. And mountains are one of the most reliable triggers of awe. When you stand at the base of a massive peak and look up at stone rising thousands of meters into the sky, your brain struggles to process the scale. It's too large, too vast. It doesn't fit into the mental categories we use for everyday objects. And that struggle produces a feeling of wonder, a sense that the world is more complex, more beautiful, more mysterious than we usually allow ourselves to notice. Mountains remind us to pay attention, to slow down, to remember that we are part of a planet with a history that stretches back billions of years, and a future that will unfold over billions more. In that way, mountains are not just physical structures. They are psychological spaces, mirrors that reflect back to us our own smallness and, paradoxically, make us feel more connected to the world. Mountains are full of surprises. Beneath the familiar image of peaks and valleys, there are phenomena that almost no one talks about. Strange, subtle, and quietly astonishing facts that reveal just how complex and dynamic mountains really are. Let's start with something called glacial earthquakes.
When a glacier moves down a mountain slope, it usually does so slowly and smoothly. But sometimes a glacier surges. A large section of ice suddenly breaks free and slides downhill, accelerating from a crawl to a sprint in a matter of hours. When this happens, the movement generates seismic waves, earthquakes caused not by tectonic plates, but by ice. These glacial earthquakes were only discovered in the last few decades, when seismologists noticed mysterious seismic signals coming from Greenland and Antarctica. The signals didn't match the pattern of typical earthquakes. They were slower, lower in frequency, and they occurred in regions with no tectonic activity. It took years to figure out what was causing them. The answer was glaciers, moving ice, massive enough to shake the ground. And now, as the climate warms, glacial earthquakes are becoming more common. Glaciers are melting faster, becoming more unstable, and surging more frequently. The mountains are responding to the changing climate in ways we're only beginning to understand.
Here's another strange fact. Mountains can trigger earthquakes far from their location.
When a mountain range erodes, it removes weight from the crust. The crust rebounds, rising upward in response. But that rebound doesn't happen instantly, and it doesn't happen uniformly. Different parts of the crust adjust at different rates, creating stress. And if that stress exceeds the strength of the rock, it releases as an earthquake. Some researchers believe that the earthquakes occurring in the Appalachians today, hundreds of millions of years after the mountains stopped growing, are partly the result of ongoing isostatic adjustment. The crust is still responding to the loss of material that's been eroded over the eons. Mountains, in other words, have long memories. They continue to influence the landscape long after they've been ground down to hills. Then there are mountains that hide entire ecosystems inside them. In several mountain ranges around the world, vast cave systems have been carved into the rock by ancient rivers. These caves are dark, isolated, and often completely cut off from the surface. And inside them, life has evolved in total darkness for millions of years. In Romania, there's a cave called Movile Cave that has been sealed off from the outside world for over 5 million years. The only entrance was discovered by accident in 1986. Inside, researchers found an entire ecosystem that survives without sunlight. The base of the food chain is not plants, but chemosynthetic bacteria that produce energy from hydrogen sulfide gas seeping from the Earth's interior. Feeding on those bacteria are worms, snails, spiders, and insects found nowhere else on Earth. Species that evolved in complete isolation, in a world lit only by the faint glow of chemical reactions. Mountains are not solid. They are riddled with voids, tunnels, and chambers. And in those hidden spaces, life persists in forms we're only beginning to catalog. Another strange phenomenon: mountain rivers that flow underground. In karst landscapes, where mountains are made of limestone, water carves elaborate networks of underground channels. Surface rivers disappear into sinkholes, flow for kilometers through darkness, and emerge from springs on the other side of the mountain. Sometimes these underground rivers are vast, wider than highways, deep enough for boats, flowing with enough force to carve cathedrals out of solid rock. In China's Guangxi province, there are mountains that are almost entirely hollow. The Li River flows through them in a labyrinth of subterranean passages, so extensive that mappers have spent decades exploring them and still haven't charted them all. Mountains are not what they appear to be. They are porous, perforated, full of hidden circulation systems carrying water, air, and life through pathways we rarely see. And here's something even stranger. Mountains hum. Not in a way you can hear with your ears, but if you place sensitive seismometers on a mountain, they pick up a constant low-frequency vibration, a hum that never stops. It's caused by ocean waves. When waves crash against coastlines thousands of kilometers away, they generate seismic energy that travels through the Earth's crust.
When that energy reaches a mountain, the mountain resonates at specific frequencies, like a tuning fork. Every mountain has its own signature frequency, its own note in the symphony of the planet. And it's always vibrating, always humming, too quietly for us to perceive, but loud enough to be measured by instruments. Mountains are not silent, they are singing. We just don't have the ears to hear them. Then there's the strange case of mountains that move sideways. Most mountains grow vertically. Tectonic forces push the crust upward and the mountain rises. But in some places, mountains slide laterally across the landscape. The entire mountain range shifts sideways, driven by the angle of the colliding tectonic plates. The Southern Alps of New Zealand are doing this right now. They're not just growing taller. They're moving northeast at about 4 centimeters per year, sliding along the Alpine Fault. Over millions of years, this sideways motion has carried rocks that formed deep underground to the surface, exposing them to erosion and creating some of the most dramatic and rapidly changing landscapes on Earth. Mountains can grow up, they can grow down, and they can grow sideways. They move in 3 dimensions, reshaping themselves and the land around them in ways that defy simple description. And perhaps the strangest mountain fact of all, some mountains glow in the dark. This phenomenon is called mountain glow, or alpenglow, and it happens at sunrise and sunset when the peaks catch the light of the sun while the valleys below are still in shadow. The mountains seem to glow with a soft, ethereal light, as if they're radiating their own luminescence. But there's also a literal form of mountain glow. In certain high-altitude regions, cosmic rays and solar radiation interact with minerals in the rock, causing them to emit faint light. It's called radioluminescence, and it's almost imperceptible to the human eye. But it's there, a gentle glow, barely visible, emitted by the stone itself. Mountains are full of light, full of sound, full of hidden motion and secret spaces. They are more complex, more dynamic, and more alive than we ever give them credit for. There are mountains that contain lakes of liquid sulfur, mountains that produce their own weather systems independent of the surrounding climate, mountains where the temperature can change by 50 degrees Celsius from base to summit, mountains where gravity is measurably weaker at the peak than at sea level due to the distance from Earth's center. And there are mountains we've never fully explored, peaks in remote regions of the Himalayas that have never been climbed, cave systems in the Andes that extend for unknown distances, valleys in Antarctica buried under kilometers of ice where mountains exist that no human has ever seen. Mountains hold secrets, and despite centuries of exploration and study, we've only scratched the surface of understanding them. There is something about mountains that affects the human mind in profound ways.
Stand at the base of a great peak and look up. Feel the cold wind on your face. Smell the thin, clear air. Listen to the silence. Not the absence of sound, but a different kind of silence. One that makes you aware of your own breathing, your own heartbeat.
This is not just scenery. This is an experience that changes brain activity in measurable ways. Researchers have studied what happens in the brain when people view images of mountains or natural landscapes. They found that these images activate regions associated with reward, memory, and spatial processing. But they also deactivate regions associated with self-referential thought. The inner monologue quiets down. The constant stream of thoughts about yourself, your worries, your plans, it fades. In its place comes a different kind of awareness, outward focused, present, open. This is the state of awe, and mountains are one of the most powerful triggers of awe that humans have access to. Awe is not just a pleasant feeling. It's a complex emotion with measurable effects on cognition and behavior. When people experience awe, they report feeling smaller, less important, more connected to something larger than themselves.
This might sound negative, but it's not. Studies show that awe increases pro-social behavior. It makes people more generous, more patient, more willing to volunteer time to help others.
Why? Because awe shifts perspective. It reminds you that you are not the center of the universe, that your problems, while real, are part of a much larger context. And that realization is strangely liberating.
Mountains provide this perspective effortlessly. They are vast, ancient, and indifferent to human concerns. They were here long before you were born, and they'll be here long after you're gone. And standing in their presence makes that fact visceral in a way that no amount of thinking can replicate.
But the psychological effect of mountains goes deeper than awe. There's a phenomenon called attention restoration theory, which suggests that natural environments help restore our capacity for focused attention. Modern life bombards us with stimuli, notifications, advertisements, conversations, tasks. Our attention is constantly being pulled in multiple directions. This is called directed attention, and it's exhausting. It depletes a cognitive resource that needs time to recover.
Natural environments provide that recovery. When you're in nature, your attention is drawn gently toward things that are inherently interesting. The shape of a tree, the sound of wind, the texture of rock. This is called involuntary attention, and it doesn't require effort. It happens automatically. And while your involuntary attention is engaged, your directed attention gets a chance to rest and recharge.
Mountains are particularly effective at this. They're complex environments. There's always something to notice. A distant peak catching the light, a pattern of shadows on a slope, the movement of clouds. Your mind engages with these details without strain, and in the process, it recovers from the fatigue of modern life. This is why people who spend time in mountains report feeling more refreshed, more focused, and more creative afterward. It's not just the exercise or the fresh air. It's the psychological effect of being in an environment that allows the mind to rest and reset. There's also something deeply human about the act of climbing. Throughout history, humans have been drawn to high places. We build towers, climb trees, scale cliffs. There's something satisfying about gaining elevation, about seeing the world from above. Evolutionary psychologists suggest this might be because elevation provided survival advantages. From high ground, you can see farther. You can spot predators, locate water sources, survey the terrain. But it's more than just utility. There's a metaphorical dimension to climbing. Ascent represents progress, achievement, the overcoming of obstacles. When you climb a mountain, you're not just moving through physical space, you're moving through a narrative, starting at the bottom, facing challenges, pushing through fatigue, and finally reaching the summit, the peak, the culmination. And from the summit, you can look back at the path you took. You can see how far you've come. And that perspective, literally and metaphorically, is deeply rewarding. This is why mountaineering is not just a sport. It's a practice, a discipline, a way of engaging with the world that tests your limits and reveals something about yourself in the process. But mountains also inspire humility. No matter how skilled a climber you are, the mountain can kill you. Weather can turn in minutes. Avalanches can occur without warning. A single misstep can be fatal. Mountains do not care about your ambitions. They do not bend to your will. You are a guest in their domain, and you survive only if you respect the rules. This humility is rare in modern life. We live in environments we've designed for safety and comfort. We control temperature, light, food, water. We've insulated ourselves from the unpredictability of nature. But in mountains, that insulation is stripped away. You are exposed, vulnerable, dependent on your own skill and the mercy of conditions beyond your control. And that exposure is clarifying. It reminds you of what matters, of what's essential. When you're on a mountain, worrying about email or social media or any of the trivial concerns of daily life seems absurd. What matters is, do I have enough water? Is the weather holding? Can I make it to shelter before dark? Mountains cut through the noise of modern existence and bring you back to basics. And there's something profoundly calming about that simplicity. But perhaps the most interesting psychological effect of mountains is something called the overview effect. This term was coined to describe the shift in perspective that astronauts experience when they see Earth from space. They report feeling a sudden, profound awareness of the fragility and interconnectedness of life on the planet. National borders disappear. Conflicts seem petty. The sense of separation between self and world dissolves into a feeling of unity. Mountains offer a scaled-down version of this effect. When you stand on a summit and look out over vast expanses of land, you see the world as a connected whole. Rivers winding through valleys, forests spreading across slopes, towns and cities nestled in the lowlands, tiny and distant. You see how everything fits together, how the landscape is not a collection of separate places, but a single system, continuous and alive. And in that moment, your sense of self shifts. You're not separate from the world. You're part of it, one small piece in an unfathomably large and complex whole. Mountains give us this gift. They remind us of where we belong.
Mountains are changing, faster now than they have in millennia. Glaciers that have existed for thousands of years are melting. Permafrost that has held mountains together is thawing. Rockfall and landslides are increasing in frequency and scale. Ecosystems that evolved over millions of years are shifting, collapsing, or disappearing altogether. This is not normal geological change. This is change driven by human activity, by the warming of the planet, and its effects are visible on every major mountain range on Earth. Let's start with the glaciers. Glaciers are rivers of ice that form when snowfall exceeds melting over many years. The snow compacts into ice, and gravity pulls the ice downslope. Glaciers are slow, patient. They carve valleys, sculpt peaks, and supply water to billions of people.
But they are disappearing.
In the Himalayas, glaciers have lost about 40% of their ice mass over the past century. In the Alps, the loss is even greater. Some estimates suggest that by the end of this century, many alpine glaciers will be gone entirely. The glaciers of Glacier National Park in Montana have shrunk from over 150 in the mid-1800s to fewer than 25 today. Some projections suggest that by 2030, there may be no glaciers left in the park at all.
This is not just an aesthetic loss. Glaciers are water reservoirs. They store water as ice during cold periods and release it during warm periods. They provide a buffer against drought. Without them, the rivers they feed will become seasonal, flowing only when rain falls, drying up during summer when water is needed most. Cities, farms, and ecosystems that depend on glacial meltwater will face crises: water shortages, crop failures, conflict over dwindling resources. And it's already beginning. In the Andes, communities that have relied on glacial meltwater for centuries are watching their sources disappear. In Central Asia, nations are arguing over water rights as the glaciers that feed their rivers shrink year by year. In the Himalayas, entire villages are being forced to relocate as glacial lakes expand and threaten to burst through their natural dams, unleashing catastrophic floods. But glacial melt is only part of the story. Mountains are also losing their permafrost. Permafrost is ground that remains frozen year-round. In high mountains, permafrost acts like glue, holding loose rock and sediment together. But as temperatures rise, permafrost thaws. The glue melts, and the mountainside becomes unstable. Rockfalls that once occurred every few decades are now happening every few years. Entire slopes are slumping downward. In some cases, massive sections of mountains are collapsing, sending debris flows racing down valleys, destroying everything in their path. In 2017, a massive rock slide in the Swiss Alps sent 3 million cubic meters of rock tumbling down the slope. It was triggered by permafrost thaw, and it was not an isolated event. Similar collapses have occurred in the Himalayas, the Rockies, the Andes, and virtually every major mountain range on the planet. Mountains are becoming more dangerous, more unpredictable, and the people who live in their shadow are bearing the cost.
But the changes are not just physical, they're ecological.
Alpine plants and animals are adapted to cold. As temperatures rise, they move upslope, chasing the conditions they need. But there's only so much mountain to climb. Eventually, they run out of habitat. They reach the summit and have nowhere left to go. This is called summit trapping, and it's pushing many alpine species toward extinction. Pikas, small mammals that live in rocky alpine habitats, are disappearing from lower elevations and concentrating at higher and higher altitudes. Some populations have already gone extinct locally. Plants that once dominated alpine meadows are being replaced by species from lower elevations that can tolerate warmer temperatures. Insects, birds, and fungi are all shifting their ranges, creating new ecosystems that have never existed before. We don't know what these new ecosystems will look like. We don't know which species will survive and which will disappear. But we know that the mountains of the future will be different from the mountains of the past. And yet, even as mountains change, they continue to rise. Tectonic forces do not stop because the climate is warming. The Himalayas are still growing. The Andes are still being pushed upward. The Alps are still responding to the ancient collision of Africa and Europe. In that sense, mountains are resilient. They have endured ice ages and warm periods. They have been ground down by glaciers and rebuilt by tectonic uplift. They have witnessed the rise and fall of countless species, including perhaps the rise and fall of human civilization. Mountains will survive. The question is, in what form? And what will be lost along the way? There's a poignant beauty in this. Mountains are both fragile and eternal. They change on human timescales, losing glaciers and ecosystems. But on geological timescales, they endure, rising and falling in cycles that dwarf our existence. And perhaps that's the most important lesson mountains teach us. Change is inevitable. Loss is real, but continuity persists. The processes that created mountains billions of years ago are still operating today. The forces that shape the planet are still at work, and long after human civilization is gone, mountains will still be here, rising and falling, shaped by wind, water, ice, and time. We are witnessing one chapter in the long story of mountains, a chapter marked by rapid change and uncertainty. But it is not the final chapter. Mountains have survived worse, and they will continue, in some form, long into the future. Our task is not to preserve mountains as they are. That's impossible. Our task is to understand them, to respect them, to minimize the harm we cause, and to remember that we are part of the mountain's story, not separate from it. Mountains are not what we think they are. They are not permanent fixtures of the landscape, frozen in time. They are living processes, events unfolding over millions of years. They rise from the depths of the earth, shaped by forces beyond our perception. They erode grain by grain, returning to the sea. They create climate, shape ecosystems, and guide the flow of water and wind. They are ancient, yet constantly changing. They are massive, yet fragile. They are indifferent to humanity, yet central to our history, our psychology, and our survival. Mountains are bridges between the surface and the deep earth, between past and future, between the human and the planetary. And when you stand in the presence of a mountain, you are standing at the intersection of geology, biology, and time itself. You are witnessing the slow, patient unfolding of processes that began before life and will continue after life. Mountains teach us humility. They remind us that we are small, brief, and interconnected with systems far larger than ourselves. But they also inspire wonder. They show us that the world is more complex, more beautiful, and more mysterious than we usually allow ourselves to see.
So, the next time you see a mountain, pause. Look at it not as a static object, but as a story. A story of stone rising from the depths, of ice carving valleys, of life adapting to extremes, of wind, water, and time shaping the world.
And remember that you are part of that story.
If you enjoyed this journey into the hidden life of mountains, we'd love for you to like this video, subscribe to Infinite Science, and join us as we continue exploring the quiet wonders of the universe. There are so many more mysteries waiting to be uncovered.
Until next time, keep looking up, keep asking questions, and never stop being amazed by the world around you.